tidal locking occurs when, over the course of an orbit, there is no net transfer of angular momentum between an astronomical body and its gravitational partner. This state can result from the gravitational gradient between two co-orbiting bodies acting over a sufficiently long period of time. In the case where the orbital eccentricity is exactly zero, tidal locking results in one hemisphere of the revolving object constantly facing its partner, an effect known as synchronous rotation. For example, the same side of the Moon always faces the Earth, although there is some libration because the Moon's orbit is not perfectly circular. A tidally locked body in synchronous rotation takes just as long to rotate around its own axis as it does to revolve around its partner. Usually only the satellite is tidally locked to the larger body. However, if both the mass difference between the two bodies and the distance between them are relatively small, each may be tidally locked to the other. This is the case for Pluto and Charon. This effect is employed to stabilize some artificial satellites. Mechanism: the change in rotation rate necessarily to tidally lock a body B to a larger body A is caused by the torque applied by A's gravity on bulges it has, induced on B by tidal forces. The gravity of body A produces a tidal force on B that distorts its gravitational equilibrium shape slightly so that it becomes elongated along the axis oriented toward A, and conversely, is slightly reduced in dimension in directions orthogonal to this axis. These distortions are known as tidal bulges. When B is not yet tidally locked, the bulges travel over its surface, with one of the two high tidal bulges traveling close to the point where body A is overhead. For large astronomical bodies that are nearly spherical due to self-gravitation, the tidal distortion produces a slightly prolate spheroid, i.e. an axially symmetrical ellipsoid that is elongated along its major axis. Smaller bodies also experience distortion, but this distortion is less regular. The material of B exerts resistance to this periodic reshaping caused by the tidal force. In effect, some time is required to reshape B to the gravitational equilibrium shape, by which time the forming bulges have already been carried some distance away from the AB axis by B's rotation. Seen from a vantage point in space, the points of maximum bulge extension are displaced from the axis oriented toward A. If B's rotation period is shorter than its orbital period, the bulges are carried forward of the axis oriented toward A in the direction of rotation, whereas if B's rotation period is longer, the bulges instead lag behind, because the bulges are now displaced from the AB axis. A's gravitational pull on the mass in them exerts a torque on B. The torque on the A-facing bulge acts to bring B's rotation in line with its orbital period, whereas the back bulge, which faces away from A, acts in the opposite sense. However, the bulge on the A-facing side is closer to A than the back bulge by a distance of approximately B's diameter, and so experiences a slightly stronger gravitational force and torque. The net resulting torque from both bulges, then, is always in the direction that acts to synchronize B's rotation with its orbital period, leading eventually to tidal locking. Orbital changes. The angular momentum of the whole AB system is conserved in this process, so that when B slows down and loses rotational angular momentum, its orbital angular momentum is boosted by a similar amount. This results in a raising of B's orbit about A in tandem with its rotational slowdown. For the other case where B starts off rotating too slowly, tidal locking both speeds up its rotation and lowers its orbit. Locking of the larger body. The tidal locking effect is also experienced by the larger body A, but at a slower rate because B's gravitational effect is weaker due to B's smaller mass. For example, Earth's rotation is gradually slowing down because of the Moon. by an amount that becomes noticeable over geological time as revealed in the fossil record. The process is still happening and has significantly slowed down the rotation of Earth over time. Current estimations of this has helped lengthen the Earth day from about 6 hours to the current 24 hours. Currently, atomic clocks show that Earth's day lengthens by about 15 microseconds every year. Given enough time, this would create a mutual tidal locking between Earth and the Moon, where the length of a day has increased and the length of a lunar month has shortened until the two are the same. However, Earth is not expected to become tidally locked to the Moon before the Sun becomes a red giant and engulfs Earth and the Moon. For bodies of similar size, the effect may be of comparable size for both, and both may become tidally locked to each other on a much shorter time scale. An example is the dwarf planet Pluto and its satellite Charon. They have already reached a state where Charon is only visible from one hemisphere of Pluto and vice versa. Pluto is roughly the same age as the planets in the solar system. Rotation-orbit resonance. Finally, in some cases where the orbit is eccentric and the tidal effect is relatively weak, the smaller body may end up in a so-called spin-orbit resonance rather than being tidally locked. Here, the ratio of the rotation period of a body to its own orbital period is some simple fraction different from 1 to 1. A well-known case is the rotation of Mercury, which is locked to its own orbit around the Sun in a 3:2 resonance. Many exoplanets are expected to be in spin-orbit resonances higher than 1:1. A Mercury-like terrestrial planet can, for example, become captured in a 3:2, 2:1, or 5:2 spin-orbit resonance, with the probability of each being dependent on the orbital eccentricity. Occurrence. Moons. Most significant moons in the solar system are tidally locked with the primaries, because they orbit very closely and tidal force increases rapidly with decreasing distance. Notable exceptions are the irregular outer satellites of the gas giants, which orbit much farther away than the large well-known moons. Pluto and Charon are an extreme example of a tidal lock. Charon is a relatively large moon in comparison to its primary and also has a very close orbit. This results in Pluto and Charon being mutually tidally locked. Pluto's other moons are not tidally locked. Styx, Nix, Kerberos, and Hydra all rotate chaotically due to the influence of Charon. The tidal locking situation for asteroid moons is largely unknown, but closely orbiting binaries are expected to be tidally locked, as well as contact binaries. The Moon's rotation and orbital periods are tidally locked with each other, so no matter when the Moon is observed from Earth, the same hemisphere of the Moon is always seen. The far side of the Moon was not seen until 1959, when photographs of most of the far side were transmitted from the Soviet spacecraft Luna 3. Despite the Moon's rotational and orbital periods being exactly locked, about 59% of the Moon's total surface may be seen with repeated observations from Earth due to the phenomena of libration and parallax. Librations are primarily caused by the Moon's varying orbital speed due to the eccentricity of its orbit. This allows up to about 6 degrees more along its perimeter to be seen from Earth. Parallax is a geometric effect. At the surface of Earth we are offset from the line through the centers of Earth and Moon, and because of this we can observe a bit more around the side of the Moon when it is on our local horizon. Planets. It was thought for some time that Mercury was in synchronous rotation with the Sun. This was because whenever Mercury was best placed for observation, the same side faced inward. Radar observations in 1965 demonstrated instead that Mercury has a 3:2 spin-orbit resonance, rotating 3 times for every 2 revolutions around the Sun, which results in the same positioning of those observation points. Modeling has demonstrated that Mercury was captured into the 3-2 spin orbit state very early in its history, within 20 million years after its formation. Venus's 583.92-day interval between successive close approaches to Earth is equal to 5.001444 Venusian solar days, making approximately the same phase visible from Earth at each close approach. Whether this relationship arose by chance or is the result of some kind of tidal locking with Earth is unknown. Proxima b, the Earth-like planet, discovered in 2016 that orbits around the star Proxima Centauri, is tidally locked, either in synchronized rotation or otherwise expresses a 3-2 spin orbit resonance like that of Mercury. Stars, close binary stars throughout the universe, are expected to be tidally locked with each other, and extrasolar planets that have been found to orbit the primaries extremely closely are also thought to be tidally locked to them. An unusual example, confirmed by most, is Tidal Bulges, a star tidally locked by a planet. The tidal locking is almost certainly mutual. List of known tidally locked bodies. Solar System. Extrasolar Tidal Bulges is known to be locked to the close-orbiting giant planet Tidal Bulges b. Bodies likely to be locked. Solar System. Based on comparison between the likely time needed to lock a body to its primary, and the time it has been in its present orbit, a number of moons are thought to be locked. However, the rotations are not known enough. These are probably locked to Saturn, probably locked to Uranus, probably locked to Neptune. Extrasolar Gliese 581 c, Gliese 581 grams, Gliese 581 b, and Gliese 581 e may be tidally locked to their parent star Gliese 581. Gliese 581d is almost certainly captured either into the 2-1 of the 3-2 spin orbit resonance with the same star.